Somewhere right now, a telescope is scanning the night sky, and a piece of software is quietly comparing thousands of images, looking for a single point of light that moved when it shouldn't have. That's how it always starts, not with an alarm, not with a control room lighting up red. With a tiny, automated flag on a routine scan, buried among thousands of other objects that turn out to be nothing. Somewhere between that quiet flag and a genuine global emergency, there's an entire system most people have never heard of, built specifically for this one purpose. Tested for real and already used at least once. On something that turned out to actually matter. Here's what actually happens, step by step. From the moment a telescope spots a killer asteroid, to the moment we'd either breathe a sigh of relief or launch a spacecraft to stop it. Step 1. Detection. Every night, a handful of automated survey telescopes, mainly Atlas and Pan-STARRS, funded by NASA, scan huge portions of the sky, photographing the same regions repeatedly. Software compares each new image to the last, hunting for anything that shifted position against the fixed background of stars. Most flagged objects are already known asteroids, or satellites or noise. But every so often, something new shows up, an object nobody has ever tracked before. Step 2. The object gets reported to the Minor Planet Center, the global clearinghouse that catalogs every new asteroid or comet discovery on Earth. Within hours, its position gets logged, and a preliminary, extremely rough orbit gets calculated from just a handful of observations. At this stage, the uncertainty is enormous. With only a few hours of data, we don't know a precise path, we know a wide range of possible paths. Like a cone spreading out from today into the future. Earth might be inside that cone, Earth might not be, nobody knows yet. This is exactly what happened with 2024 YR4, discovered in late December 2024 by a telescope in Chile. Within days, it landed on NASA's automated risk monitoring system, called Sentry, which continuously recalculates the odds for every newly discovered object with any plausible future close approach to Earth. Sentry runs these calculations automatically, around the clock, for hundreds of objects simultaneously, using a technique that essentially simulates thousands of slightly different possible orbits at once, based on the range of uncertainty in the observations so far, and checks how many of those simulated futures would result in an actual impact. Step 3. Risk classification. Once an object is judged to have any measurable chance of impact, it gets assigned a rating on the Torino Scale, a simple 0 to 10 system designed specifically to communicate risk to the public without causing needless panic. 0 means no concern, 10 means a certain, civilization-altering impact. The vast majority of newly flagged objects get quietly downgraded to 0 within days. As more observations narrow down that cone of uncertainty and Earth falls outside it. 2024, YR4 didn't get downgraded right away. Instead, its probability kept climbing as more data came in, first to 1.2%, then 1.6%, eventually peaking at 3.1% in February 2025. That made it the highest Torino Scale rating, a 3, assigned to any object in over a decade. It wasn't the first time this exact drama played out. Back in 2004, an asteroid called Apophis briefly reached a Torino Scale rating of 4, still the highest ever recorded, with an initial 2.7% chance of impact in 2029. Additional observations eventually ruled that out completely too. Apophis will still pass remarkably close to Earth in April 2029, closer than some satellites orbit. But scientists now know with near certainty that it will miss. That 2029 flyby is actually being used as a rare, real opportunity to study a large asteroid up close, using ground-based telescopes and a dedicated spacecraft, without needing an actual emergency to justify the observation. Step 4. This is the point where the system stops being purely automated and international coordination kicks in. Two organizations you've probably never heard of activate. The International Asteroid Warning Network, which shares data between observatories across the entire planet to get as many independent observations as fast as possible. And the Space Mission Planning Advisory Group, which exists specifically to coordinate what a real deflection mission would look like, if one were ever needed. At this stage, astronomers race to get every available telescope, everywhere in the world, pointed at the object, because more observations mean a tighter, more precise orbit, and a tighter orbit almost always means the impact probability either collapses to zero, or far more rarely, gets confirmed as real. Step 5. Refining or escalating. In the case of 2024, YR4, additional observations through February and March of 2025 eventually narrowed its future path enough to rule out an Earth impact entirely for 2032. The odds dropped back to zero for our planet specifically. But here's the twist most coverage at the time didn't fully explain. The same refined data revealed a small, separate chance, around 4% at its peak, that the asteroid could strike the Moon instead, in December 2032. That risk is still being monitored today, and won't be fully resolved until the asteroid becomes observable again in 2028. Step 6, the one that almost never happens but exists for a reason. If an object's probability doesn't drop to zero, and instead gets confirmed as a real threat with enough lead time. The Space Mission Planning Advisory Group's plans move from theory to action. This is exactly the scenario NASA already tested for real, not hypothetically. In September 2022, with the DART mission, deliberately crashing a spacecraft into an asteroid moonlet called Dimorphos at over 22,000 kilometers per hour, specifically to prove that a kinetic impact could measurably change an asteroid's trajectory. It worked far better than expected. Dimorphos's orbit around its parent asteroid shortened by about 32 minutes, confirming that with enough advance warning, humanity has a real, tested method to nudge a threatening object off its collision course before it ever becomes one. The follow-up mission Hera, launched by the European Space Agency in October 2024, is now on its way back to Dimorphos specifically to measure exactly how that impact reshaped the asteroid up close, data that would directly inform how fast and how precisely a real future deflection mission could be planned. So here's what the full process actually looks like, start to finish. An automated telescope flags a moving point of light. The Minor Planet Center catalogs it and calculates a rough, uncertain orbit. NASA's Sentry system starts tracking its risk continuously. If the risk is real, a Torino Scale rating gets assigned, and the world's telescopes turn toward it together. Almost always, more data drives the risk back down to zero within weeks. In the rare case it doesn't. An international network built specifically for this moment is ready to move from tracking to action, and for the first time in human history, we've already proven that action can work. The strange part is how quiet this entire system usually is. Most people never hear about the asteroids that get ruled out, and there are dozens flagged every single year that go through exactly this process. Reach a moment of real uncertainty, and then quietly resolve to zero without ever becoming a headline. 2024, YR4 became a headline because, for a few weeks in February 2025. It climbed higher on that scale than almost anything discovered in the last decade. Not because the system failed. Because the system worked exactly as designed: flag it, track it, refine it, and only sound the alarm once the data actually justifies one. We are the first generation of humans who built that system at all. Every civilization before us that looked up at a strange, moving light in the sky had no telescope precise enough to calculate its path, no international network to share the data, and no spacecraft capable of doing anything about it. Even if they'd known exactly what was coming, we might be the first generation who never has to find out the hard way. Not because the danger doesn't exist, it always has, but because, for the first time, something is actually watching, calculating, and, if it ever truly needs to, ready to act. Beyond the visible, beyond what you can see, but never beyond what you can understand. Subscribe, because next time we go beyond again.